Chen is a Nanyang Associate Professor with the School of Computer Science and Engineering in Nanyang Technological University, Singapore. He also serves as the Director of OpenMMLab at NTU and Co-Associate Director for S-Lab in NTU. And he's also an Adjunct Associate Professor at the Chinese University of Hong Kong. Let us welcome Chen to give his talk.
Okay, thanks Chen for the kind introduction. So the title of my talk today is Generative Latent Bank for Large Vector Image Super Resolution. So this paper is accepted as an oral paper in CVPR, and it will be presented in session 11, so this Thursday. So before I start my presentation, just would like to introduce my lab. MMLab at NTU was formed in 3 years ago, okay, with research focus on computer vision and deep learning. So we are working on various interesting research topics, especially on low-level vision, content editing and generation, 3D scenes understanding and reconstruction. So now we have 4 faculty members and more than 25 research staff and PhD students. And this year we have 18 papers accepted in CVPR, and some of them they are results of collaboration with Science Time as well as Chinese University of Hong Kong and also other universities. So if you are interested, you can go to this link. We share the schedule of each presentation and you can have a look. Okay, so our team has been working on the problem of image and video super resolution for the last few years. And it's a very interesting and exciting topic. So we started the topic back in 2014, where we proposed the first CNN for super resolution. We called it SRCNN. Then after that, we have been improving our methods over the years and extending to various applications such as depth map super resolution and also phase hallucination. So the model, the very preliminary model, SRCNN alone already enjoys a lot of applications. And after that, we also extend our work, our horizon to video super resolution. Notable methods include EDVR and basic VSR that we proposed this year. It will also be presented in CVPR this year. And with these methods, we won several champions in entire competition, which is an important challenge for image restoration and video enhancement. One of the important direction of super resolution is to enhance the texture details. And we want the texture details to be faithful and to be realistic. So 2 years ago, we proposed a method called ESRGAN. It is a network improved from SRGAN. And we basically improved the architecture, the perception loss, and adversarial loss. And it becomes a very popular tool for remaster the various classic games such as Resident Evil and Doom. And last year, we proposed a method called Deep Generative Prior in ECCV 2020. So basically, we make use of Gan Inversion as a way to enhance the details of a downsample image without training. You basically rely on a pre-trained GAN to do the job. And this year, we proposed Glean, so which is a better way that can perform large-scale super resolution with very good details. So I'm going to present this work in this talk. So before I go over the details, so I want to show some results. So this is the input, which is heavily compressed. And by using conventional methods, even with adversarial loss, it will be very difficult to recover all the details. But with Glean, you can see that even you can restore the details even for like facial hair, eyebrows, things like that. And this is another example. You can see that this is heavily compressed and contain noises as well. And all these samples are corrupted by some unknown downsampling kernel. So we do not actually know what the downsampling kernel is. And the results are still pretty good. Yeah, the I slashes and the T's are all recover very well. So let me get back to the introduction and then introduce our method. So we know that the objective of super resolution is to reconstruct the high resolution image given the low resolution input. So typically in research, we are dealing with upscaling factor of 4 times or 8 times at most. So the problem will be getting more difficult if we want to go for like higher magnification factors, like 64 times. So which typical SR methods will fail because they cannot handle, they cannot recover the details, and the textures or the high frequency components are lost during the downsampling. So for instance, in this case, we only have a 16 by 16 image. So it will be very hard for us to upscale it 64 times larger using conventional methods. So since the problem is like severely unspecified, then what we need to do is that we need to introduce some informative or meaningful priors in this setting so as to restore those texture details. So this is the result of our method. You can see that we can recover very good details and verify textures. So we basically make use of Gan. Okay, I'll talk about how we make use of Gan later. So basically there are there are 2 main approaches to deploy Gan for super resolution. So the more common paradigm here is to train a generator to handle the upscaling task, where you basically introduce adversarial training and you use a discriminator to differentiate what is fake and what is a true. Yeah, fake basically is the super resolution result, and true would be the real image. And another possible way is to deploy Gan inversion. So by Gan inversion, you basically invert the generation process of a pre-trained GAN by mapping an image back to the latent space. And then you try to find optimal latent vector, and then you reconstruct the image. So you get a better image. So let me talk about the first paradigm, which conventional networks. So these conventional networks, basically, they take encoder and decoder structure. We basically use the encoder to extract features, and the decoder would take the features and perform upsampling and reconstruction. So then we get the results like this. And to train this network, we usually use a combined objective with pixel-wise loss, for example, mean square error, and also adversarial loss. And in this case, we observe that this kind of architecture basically have to do 2 things simultaneously. Basically, it needs to capture the natural image characteristics, which is induced by this adversarial loss. At the same time, it has to maintain the fidelity to the ground truth. That means it has to obey the structure of the input image. So doing these 2 things together is usually complicated and it's not easy. So what we observe is that with this kind of paradigm, you actually limit the capability of the network to approximate the natural image manifold. So we apply the ESR GAN in this case for large-scale super resolution. And as you can see, yeah, we can more or less recover the structure. But if you look at the details and you compare with the ground truth, so all the fine details are actually off from the ground truth. And this is what you don't want. And can we solve this problem? Yeah, then comes up a second paradigm where people try to use Gan inversion. So we know that Gan is a good approximator for natural image manifold. Yeah, and people have later people have used it for for various image restoration tasks. So basically, to apply Gan inversion, yeah, we typically reconstruct a target image. Yeah, I mean, using Gan inversion for restoration, we typically reconstruct a target image by optimizing over the latent vector Z over here using this equation. So here S hat is our target image, which is corrupted, and G is the fixed generator, and G and theta are the latent vector and the generator parameters respectively. So there should be a video. Anyway, yeah, the video is playing. So basically, the purpose of performing Gan inversion here is to find an image in Gan image manifold, after which it is degraded, matches exactly to our degraded target image. So here, the assumption is that the degradation function is known and it is also differentiable. And since the image prior in the Gan tends to generate natural looking images, the reconstruction will generate an image with high resolution. So this paradigm is also employed in our DGP paper, which is published in ECCV 2020. So there are some problems, shortcomings of these methods. Basically, we know that the low dimensional latent vectors is basically insufficient to preserve all the details. Imagine we want to recover 1000 by 1000 resolution image, and with a compressed vector of, for example, 256 dimensions, it will be very hard for us to keep the details. And usually, when we do Gan inversion, it involves expensive iterative optimization. So these are the two main shortcomings of Gan inversion. And we wonder whether we can, we try to solve it using Green. Here we show some results of performing Gan inversion. Particularly, we show the result of Pulse, which is a popular method that performs inversion. So given this low resolution image, Pulse basically search the manifold for a plausible high resolution reconstruction. Now, as you can see, it is basically far away from the ground truth. Yeah, it's realistic, but very dissimilar to the ground truth. So Green, which is our method, is very simple. So we basically use a pre-trained GAN in a encoder decoder structure. Basically, we plug a pre-trained GAN in between this encoder and decoder. So what we want to achieve is that we want to get realistic textures and details, and we want the output to be faithful, as in the ground truth, and has to be efficient. So the good thing about inserting a pre-trained GAN generator in between the encoder and decoder structure is that we do not need to do two things together anymore. So recall that with encoder and decoder structure, the architecture has to maintain the fidelity and also has to ensure photorealism simultaneously. But with the pre-trained GAN generator over here, it basically takes care about the photorealism aspect. And the encoder decoder only need to take care about the fidelity, to maintain the fidelity of the output. So in this way, we can do far better. And another good thing about this architecture is that it only needs to perform one single forward pass for the restoration. Yeah. So this is the detailed structure, detailed architecture of Glean. As you can see, it comprises of the encoder, the generative latent bank, as well as the decoder over here. So Here, the encoder basically extracts features from the low resolution input. So, and it provides the latent vectors, okay, in a C matrix to capture the compressed representation of the image. And that will be fed into the generative latent bank. Yeah, we call it generative latent bank. So that gives the bank with some high level information. And then to further capture the local structure of the low resolution image and provide additional guidance for the structure restoration, we also fit the multi-resolution convolutional features into the latent bank. And this architecture takes a symmetrical a model. Basically, the latent bank later also provides multi-resolution features to the decoder and to construct the output. So this decoder basically ensures better fusion. So the whole architecture here is actually inspired by the conventional notion of dictionary. So in conventional dictionary, basically need to build a finite and image-derived dictionary. But here we actually employ a pre-trained GAN as a more effective way to store priors for restoration. And this pre-trained GAN, it doesn't have to be retrained or fine-tuned. You just plug it into the encoder-decoder structure, and you only need to fine-tune your encoder and decoder structure for your target task. And let's look at some experimental results. So here we show the comparison between our method and some conventional networks like ESR GAN and SynGAN. So you can see that with ESR GAN plus, here we actually increase the capacity of ESR GAN so that the flops matches our model. You can see that the details are not really handled well compared to the ground truth, and SynGAN as well. And when we compare with Gan inversion methods like pulse and GAN prior and DGP, so you can observe that the identity has changed. Yeah, and it doesn't look like the actual people anymore. So with our method, we not only preserve the identity, but we also generate high quality textures. You can compare the output of our method to the ground truth. So this is by using a 16 times super resolution, which is considered pretty high compared to conventional settings. And to judge whether to examine our method, whether we preserve the identity, we measure the cosine similarity using our phase features. The higher, the better. So you can see that green actually outperforms all the baselines over here. And we see that green is actually robust to changes of contents. So when we train it on aligned human phases, it works very well on diverse contents like Iron Man, Mars, and also with different poses. We can still restore very well. And if you look at the pulse, basically, interestingly, you can find that pulse actually looked very similar to the input when it is at a low resolution. But when you look at the upscale output, it's actually perform very worse. So green can work in various scaling factors. We can do this for 60 times, 32 times, up to 64 times of upscaling while giving good details. And this is what we have done, I've shown earlier. And these are some additional results that we try to recover some real-world image with unknown degradations. What we are doing here is actually augment our training data with more aggressive augmentations. And we try to degrade it with various types of bullet kernel and downsampling kernel, as well as different compressions. And that allows the model to perform more in a more robust manner in real-world images. So green actually works well on various categories of images, not just faces. We have done it for cats, buildings, indoors, cars. So the bad thing is that for green, for now, the prior has to be that particular object category. Yeah, that means that if you want to restore cat images, then you have to plug in a train gun that is trained on cat. So this is one of the shortcomings of green, and I would see that it can be improved by using some class conditions and using some multi-class gun. Okay, and we did some aberration studies, yeah, to test basically the effectiveness of introducing the multi-resolution connections over here. So when we provide more connections, like 4x16 to 32 and even 64 by 64 features to the generative latent bank, then we generate better details and also maintain the structure. But if we remove all the connections over here, then what it does is that it is very similar to Gan inversion methods, that it keeps the structure, but then the details are not faithful to the ground truth. And we also test the generator decoder connections, basically the connections over here. So if we remove the connections, then no information will be passed from the bank to the decoder, and you get very bad results. So this is again then very similar to ESR GAN, where you actually do not make use the bank anymore. You will get some results like this. And decoder is important, basically to refine the details of the generations. Basically, if you remove the decoder, then you get some weird textures and some of the boundary and some details are not that good anymore. So basically, in this work, we propose a novel framework that exploits generative prior for large-scale super resolution, which has been a very difficult problem in the past. And we show that with generative bank, it can actually reconstruct high-quality images with high fidelity. And it works well with various factors, different objects, and also real-world degradations. All the codes here, the green, okay, as well as previous methods that we have discussed, SRCNN, basic VSR, UDVR, ESR GAN, they are all available in editing. So we ensure them they perform with a good quality, and it's very easy to use. You should go and have a try. And if you need pre-trained style guns or pre-trained guns, they are all available in generation. Yeah, it is very easy to use those guns in editing. You can basically use these libraries seamlessly. So here are the links, and you can go and have a try. Okay, thank you, and I'm open to questions. So while waiting, I'm showing more results over here. Any questions?
Hello.
Yes.
Hi. Thank you for the talk. I have a question. This is specifically for like face videos and others. So how does this algorithm works for like varying illumination across the screen? So for example, say the driver's face, where means we often see a hard shadow. So do you think that there is any specific challenge you see in there?
We actually do not see any big issues in like given shadows or some hard lights or some extreme illuminations. Of course, if the image is extremely dark and dim, then the algorithm might amplify some noises on the face. But in what we have tested, we observe satisfactory results. Yeah. Just that, I mean,
Thank
if
you.
your images are dark, then it might contain some noises. Then these noises might be amplified.
Okay. So means you are suggesting that if there are enough information there, so it will be enough. It will be able to reconstruct. But if it's too dark and maybe very high noise content into high spatial noise in there, then probably it might fail.
Yeah, exactly. Yeah.
Okay. Thank you.
Thank you. Okay, so we give back to Chen Kai. Yeah.
Okay, thanks to Kevin. Now we will invite Jifeng Dai to share his slides.